Let's move on. Our next speakers are MOUTON from Bureau Veritas and Linda STARINK from Lloyd's Register. They will explain what the guidelines are all about and how the end users can apply them in practice. The first speaker will be MOUTON.
Good morning. My name is MOUTON. I work in Veritas Marine and Offshore, and I come to this morning to present you the parts of the guideline, the structure of the guideline that we prepared in the project. So the guideline is part of the work package 3. The aim was to develop procedures, a guideline for the qualification of adhesively bonded hybrid joint in primary structure for marine application. It lasted 52 months, so the duration of the project. And briefly, to summarize, it's a guideline for qualification of hybrid joint. On primary structures, we wanted to reach clarity of requirement and to be applicable in a short time. What we want to go away from, the classical and maybe too much seen process of characterizing the loads, making some calculation, applying safety factor of 5, 6 to 15, and then judging the risk as acceptable. It might be rapid, it might be clear, but it's in no case it can be applied for primary structure or to a new application and innovation. On the contrary, where we wanted to go. So within Qualify, we have performed a risk analysis, not that we want to go to a systematical risk analysis, but that helps mapping the problem. So we have studied the loads, the cycling, the aggression, damage, and kind of defect, the impact of the manufacturing quality, the strengths, so the short-term strengths, as well as the fatigue and damage tolerance. We studied also the protection by sealant or by a joint or something like that, assessed by test, and the durability prior to study the monitoring inspection. And then we think that the risk can be judged as acceptable. Is it rapid? Probably not enough for some of you, of course, but it's quite clear. It's applicable to primary structure and it's applicable for new applications. So innovation is not hindered. In the guideline, the first part is the preliminary assessment. The idea is to map the characteristic of the adhesive assembly. The loads, type of loading, numbers, amplitude, the design life, what are the temperature, what is the environment and all the threats associated to the environment, what is the protection, what is the joint material, what is the process, the yard, the experience from the yard, what is the former experience in similar joint, similar material, are there possibilities of inspection, and last but not least, the safety class defined as per the DIN 2304, and also the technology maturity. From then on, we can go to the requirement definition, which is the second part of the guideline. The objective is to define upon the safety class and the technology maturity requirement level, which is the highest the uncertainties on the technology and the highest the risk on the joint, then you get the highest requirement level. This requirement level will be used to define the necessary qualification activities. So you have a requirement level and then all the boxes here come in the rest of the guideline, that's the qualification activities. This table is not defined in the guideline, the roadmap is ready, but it is to the classification society to define their own requirements. Qualification activities, so that's the core of the guideline. We have used the work of the partners in the different tasks and also the experience from the classification societies. So we have characterizations, part on strengths with the test and the calculation, durability with also strengths and calculation, the protection which was studied so as to see the efficiency, actual efficiency of the protection, the manufacturing and the in-service monitoring. In the end, the global structure of the guideline is presented on this map. You have preliminary assessment with the design capture and the definition of requirement, so qualification activities requirement, the corresponding qualification activity, which are each one part of the guideline, complementary characterization. Why complementary? Because the homologation of the adhesive will bring the first step of characterization. And upon satisfaction of this requirement, you can go forward with the adhesive joint or loop up, change the design or others. If we want to discuss about the first box, so the strengths, basically what is the strength is the fact to define the loadings on the joint, their numbers, their amplitude, so as to map the design load, the maximum load with, that may appear to a joint. This will be compared to actually the strength of the joint with the average scattering and the characteristic load, which is close to the minimum failure load. This is fairly easy through a project like Qualify by testing. It defines the margin between the load and the strength, which is indeed the safety factor. But when it comes to an actual design, you do not have access to the strengths by test because it's not possible to define a test and to perform a test for each design configuration that will happen, each design loading. So then we will need a design tool, a design calculation that will give us an estimation of the strengths. But this estimation is just an estimation, and there is an error which might hinder and maybe be damaging to the safety factors or margin, so to the safety factor. So the question of the robustness of the calculation is always at stake here. To study this robustness, we have used a methodology based on the EN 1990, which we will present here. So let's think we have adhesive bonding assembly. We build a test setup and we break it experimentally so that we get an experimental failure load with the scattering, which define the dispersion associated to the material, to the design, and to the process. Then we can make a calculation for this assembly, for the same setup as the test setup, and this calculation will predict one failure load so that we can plot within the predicted failure load to experimental failure load. In this diagram, we can plot the result. We have done that for one setup, and we can do it for different setups so as to assess the impact on the joint strengths of different loading, different configuration of design, etc. So we repeat the operation, experimental testing and calculation. We will get a cloud of points like this, which enables us to define using this method a factor to be applied on the predicted failure load so as to cover the experimental scattering, but also the calculation accuracy. This is true whatever the calculation method. It can be a very simple average stress method or a finite element cohesive element or something very complex. Then we have a large gain in confidence for the shipyard, for the owner, and for the class. Next step is the guideline for the fatigue assessment. So there are guidelines for the establishment of SN curve, but also for the validation of design by full-scale test. This is from the load histogram to the transfer, and the load histogram to the test piece, and also the associated safety factor. For the damage tolerance, there's an assessment of damage tolerance which is guided, and mainly on the definition of the initial damage, which is very important parameters in such analysis, which will depend on the inspection protocol, etc. Then we can compare the energy at the crab tip for the design load to the fatigue energy threshold that can be as it was done in Qualified, that can be experimentally determined. Finally, there's a part on characterization, the idea being to characterize the behavior of the material, of the interface, of the assembly. And it will be something on top of the homologation, which will give the partial results. And the idea is to measure the physical characteristic so as either to compare different products, adhesive A, B, C, or surface preparation A, B, C, validate the adequacy of the design of the material to the specification, for example, the glass transition temperature, and feed the simulation, like the Young modulus, the shear modulus, the strength, or the diffusion coefficient for the durability. In the end, so that's the structure of the guideline, reminded, and I presented to you the 4 first boxes, and I will leave now the floor to Linda STARINK from Lloyd Register, who will introduce you the remaining activities. Thank you and have a good meeting.
Thank you, Luc. Now we'll go to Linda's presentation.
Thank you, Luke. Good morning, everyone. My name's Linda STARINK. I work for Lloyd's Register as a non-metallic specialist, and I'm going to talk you through the second part of the guidelines. Luke's already spoken about the preliminary design capture, the requirements assessment based on the safety case, the characterisation of materials behaviour and the joint strength. I'm now going to show you how the guidelines deal with durability, protection, manufacturing and in-service inspection and monitoring to help navigate the path to requirement fulfilment. The next thing to deal with after strength is durability. We've looked so far at the analysis of performance at a single point in time and after repeated cyclic loading in the case of fatigue, but there's many properties that are actually time dependent. For example, relaxation of viscoelastic material over time can lead not only to creep, but also to changes in the pathway for diffusing materials. In an ideal world, we'd use materials and the joint designs that have been tested under all the conditions for the lifetime of the joint, but that's obviously not practical. Instead, we need to accelerate the testing by increasing parameters such as load or temperature. But we need to do this in a manageable and well understood manner that doesn't introduce erroneous behaviour. You can see here how we might increase temperature to give us different diffusion profiles. And this curve shows us how we use a master curve for creep. So we do short-term testing at different load levels, and then we can time shift that data and create a master curve so that we can predict what's going to happen at the service load, but over time. There are standard conditioning cycles around that could be used, but it's really important to understand what that conditioning cycle is actually replicating and that it's not giving you erroneous results. This graph shows a plot of reciprocal of absolute temperature against log of diffusion coefficient. The gradient of that graph is proportional to the activation energy of the process of diffusion. So if that's a linear graph, we can see that the diffusion at each of those temperatures is using the same process effectively, has the same activation energy. If the curve deviates from that, we then can understand that a different diffusion mechanism has opened up. That might be due to the rearrangement of free volume, etc., over time. If we test at these temperatures, we'll get a saturation level that isn't representative of what would have gone on in normal service conditions for accelerated time. So this is the only safe temperature, or the highest safe temperature that we can use, that we're assured is replicating what's really going on in the service temperature. Once you establish this temperature, you can then use that for your accelerated aging. So just carrying out normal gravimetric testing. This example shows at 50 degrees and 20 degrees. Here, if we look at equivalent moisture content, that's the average amount of moisture in the joint at a given time. To achieve the same level at 50 degrees takes 1 day, whereas it would take a week or 7 days at 20 degrees centigrade. So we can see there's a significant effect of accelerating that temperature, and it's the most useful tool we can look for accelerated conditions. So we can see that we can predict the percentage of moisture in a joint at accelerated temperatures, but what's actually important is where the moisture is in that joint. The guideline gives the equations that you need to work out what the moisture profile is at a given temperature and humidity over the lifetime of the joint. In this case, we've plotted it all the way up to 500 years and we still haven't reached saturation at the end of the joint. In fact, after 25 years, which is an effective ship lifetime, we're only about halfway through the joint, and that's important to give us confidence that the joint's not going to be fully wetted out in the lifetime of this particular configuration. There's other things you can do to accelerate the conditioning. Temperature's the big one, but you can do things like increasing the relative humidity so that you're pushing more moisture in and you're getting pushing further along in this moisture profile, and also taking part of the overlap length away so that you can then shift that moisture profile. Say, for example, here we've got 10 weeks of testing. We've shifted it by taking 10% of the joint away, assuming that that joint's already degraded. As you can see here that we can quite nicely replicate in 10 weeks at accelerated temperature what would happen in normal service conditions for 5 years, which gives us a nice interval for between inspections. In reality, joints won't be exposed to the environment without any kind of protection on them. So things like sealants, paints, and physical coverings can be used to protect the joint from moisture ingress and things like UV degradation. However, we consider these to be a design redundancy, i.e. they're nice to have and they give you a lot more confidence in the joint, and certainly increase the lifetime of the joint. But we need to have understood that joint and assessed it if that protection fails. The coating industry are also already familiar with this process and how we understand the effect of protection failure. The performance standard for protective coatings for cargo oil tanks and water ballast tanks has a lovely test that involves scribing a line into a coated sample, putting it in a wave tank and conditioning it for 6 months, either in water or oil, depending on the application. The idea is then when you take that out of the sample, you pick the coating away to see how far that bond is degraded between the coating and the steel. You can do the same sort of thing with a laminate, in that we can put some kind of damage into the laminate, expose it to conditioning, and then examine the interface afterwards to see if there's been any rusting under the laminate, or any decrease in the bond strength. And that can give us a good idea. There's some anecdotal evidence that there's rust creeping under composites to steel joints, and it's important to understand for your particular set of systems, for your resin system and the steel preparation that you use, that that's not going to be the case. We'd all like to think that we put our coating on, it lasts forever, but we know it doesn't. The same goes for sealant. It's important to understand if you're going to use a sealant to cover the joint and stop moisture ingress, that you assess that. There's standards out there to do that, or it can be as simple as just doing a test where you put some colour changing beads under a sealed panel and immerse it in fluid and see if that fluid then could be seen to change the colours inside the test sample. It's quite handy because you can see where leaks might be, etc. And it's a good way of just understanding the efficacy of a sealant so that you can use it for mitigation. So we've looked at what we want the design to be like. We've looked at how we test for that. What's important though is that we understand what the joint will really look like once it's been manufactured. What's in the designer's head doesn't always match what's manufactured on the shop floor for obvious reasons. It's important, therefore, that when we're testing samples, that they're always made under manufacturing conditions and not in lab conditions. They need to account for the conditions that might be seen in a shipyard, for example. What's also important is that we understand the influence that human error has on bond integrity. Unless you can fully automate your process, which is very unlikely under large ship conditions, then the quality of the joint is entirely dependent on your operator skills. We're creating in this example a joint that has structural performance. So we're joining two structures together and expecting that joint to behave the same way that we would if we welded two components together. So it's important that when we assess the skills of the operator, that we've assessed that in a manner similar to that we would use for a welder. The European Abrasive Bonder qualification gives a really good training outline for what we'd expect to see for operators, and not just operators, for designers and for manufacturers. It's really important that everybody involved in that process understands how important things like surface cleanliness, surface preparation, clamping, etc., cure cycles, all of those have an influence on the integrity of the joint. It's also important to talk to the adhesive supplier. They know their product better than anybody else does. They've done all the development. If they're brought in at the early stages of the manufacturing prototyping, they can start solving problems so that you get to a point where your joint's actually making the most use of that adhesive and you've got the optimum properties. The final section of the guideline sets out the role of non-destructive examination techniques. This is to establish both the as-built quality and to look for changes in performance during service. That could be either through structural health monitoring or intermittent NDE examination. Visual inspection is always going to be an important part of that. Nothing tells you better how a joint's performing than having a good look at it and looking for any signs of rust, etc. The guidelines set out the protocol for validating those techniques, though. What's important is that we understand exactly what we're looking for and that we have assured that the kind of defects we think we're looking at are actually represented by the signals that we're getting back from that NDE technique. In the past, the aerospace industry have looked at things like critical floor size. They establish a level of defect that their design can cope with, and then they look for an inspection technique that can identify that defect. But we're looking at a more pragmatic approach. Because of the variety of marine composites and the fact that some of them are highly attenuative, it's important for us to look at what size of defect we can actually detect now. Once we've established what that is, then we have to make sure that that design process is robust enough to cope with that size of defect. So we need to test with that level or model with that level of defect in place and make sure that not only the performance is sufficient at that stage, but also that that defect can't grow before the next inspection point. If we get a defect that grows quickly, we can obviously get critical failure, and we must prove by testing and modelling that that's not going to be the case. At the moment, we're limited in the processes, especially for things like adhesive joints, because things like kissing disc bonds give us all a headache, obviously. As those techniques improve, the guidelines are set out in a way that they'll move with that improvement in technology, meaning that as we can see smaller and smaller defect size and we have more assurance in what we're actually looking for, then we can start really pushing those design stress levels, and that we've got a lot more confidence in what the joint's actually doing. There's a lot of work ongoing on this still, and we're going to be updating the guidelines as these new techniques occur. So now you've seen all the elements of the guideline document. The intention is to have the document available by Christmas in the form of Output 7 for this programme. The Qualify projects developed clear pathways for qualification of hybrid joints. We did this based on analysis of two very different joint types, so both a thin brittle material and a thick ductile material. Doing this means that the guidelines are more flexible. It means that we can use them for a full range of joint designs and applications and behavioural types. That's really important, that we're not stuck to a very narrow remit, and we've proven in this that that's possible. Some decisions are still always going to be carried out on a case-by-case basis, depending on things like statutory regulations for specific applications or really novel concepts that we need to research further. But the guidelines define the goals of the process and give advice how to mitigate the risk to an acceptable level. There's still some work ongoing, particularly in the SHM and NDE, but we'll integrate that as time goes on. For Luke and myself, our work is now to go and disseminate these guidelines widely within our own organisations. The ultimate aim is that we integrate them into our rule sets. Once we understand what the breadth of adhesive joint design and configuration is, then we can start to put prescriptive rules or goals that we can work to. Thank you for listening. We hope this has given you a good overview of what the guidelines contain. I'm going to leave our partners now to tell you a little bit more about some of the actual work that went on in Qualify. Thank you.
Thank you very much, Luke and Linda. That was a great overview of the guidelines. I have a question. So where are going the end users be able to access these guidelines?
It's always difficult when there's two people answering. So from a Lloyd's point of view, they'll be accessible on our website, basically. You'll just have to look for guidelines for adhesive joints, and ultimately that's where they'll be.
And Luke?
Yeah. Yes, similarly, we have a page on Qualify dedicated to Qualify research project on the Bureau Veritas website. So I suppose that that would be the best place to present it.
Okay, great. Thank you. Are there more questions, maybe from the audience or online? No, not yet.